Right. Okay. So test whether this flow is incompressible or not. Okay. So we are given expression for the components of the velocity in the velocity field, the u, v, and w. Right. So then one would be okay, part one. Example. I call example 2 topic 6, right? Topic 6. Okay? Okay. What? So how do we start? How do we start? Anybody? Let's continue the tutorial. Anybody? Exactly. Differentiate. The rest of people I have no idea. Differentiate with what? We want respect. What we want? Okay, the way is very simple. You are given u, v, and w, right? You are given u, v, and w, right? Where is it? 67. Okay, so what you need is therefore to find each term. You are given u, v, w. So you differentiate u with respect to x, differentiate v with respect to y, differentiate w with respect to z. You add it all together. If it is equal to 0, then the flow is incompressible. If it's not equal to 0, it is compressible. Okay, so let's do that. So what's the value of x? Okay, so what's del v? Ly. Negative 1. Del w? Del z? 0. So therefore, so therefore, del u, del x, plus del u, del y, plus del w, del z, equal to 0. So therefore, incompressible. Okay, flow is incompressible. That's one. Okay. Okay, so two, by determining the expression of the angular velocity, omega, angular velocity omega, by determining the expression for the angular velocity components of the flow, make a decision of whether the vortices might present in the flow field. Now, vortices, for example, you have a flow, flow past a body. You put a body in your flow and there's this flow coming in. Okay, the flow will separate. Okay, so when the straight lines go over here and because the shape of the object, there will be vortices. If there are vortex or vortices, it means that there is an angular velocity of the fluid elements. Okay, they just go around rolling and they just this is turbulent and a lot of these fluid particles will just rotate. Okay, so these are actually vortices due to turbulence and because of the obstruction in the flow field. So the fluid elements therefore have angular velocity components. So how do we actually find out whether by determining the expression for the angular velocity, whether there are vortices or not? Okay, now I'll just give you now the expression for the angular velocity. Yeah? Okay, the angular velocity about the x-axis. About the x-axis, I call it omega x. Okay, angular velocity about x-axis is given by this expression, half del w del y minus del v del z. Del z, don't talk that, del z. Okay? We just accept this for the time being. Half del w del y minus del v del z. Okay? And of course, if you use the expressions given to us in the question, what's del w del y minus del v del z? Del w del y is 2x plus 2y. Okay? And del v del z is 1. So it's 1 and it's a minus in front. So there it is. So we know that this is not equal to 0. So similarly, angular velocity about the y-axis, and we call it omega y, is given by this expression here, half of del u del z minus del w del x. This is omega, and this is w. Okay? And from the expression given to us, the uv and w expression, you do the necessary differentiation. Del u del z is 2z, and del w del x is 2y. So again, this is not equal to 0. Okay? And then, similarly, you can write an expression for the angular velocity about the z-axis. Z-axis, call it omega z. Okay, and it's given by half del v del x minus del u del y. Okay, and then you differentiate the given expressions accordingly. You get half of 1 minus 1, which is 0. You know your 1, 0 term, the rest are non-zero. Okay? So, which means that vortices are present. Okay? As long as you get 1 not equal to 0, vortices are present already. Okay? Therefore, we say that vortices present. In flow field. In the flow field. Okay? You have 2 non-zero. I say 1 non-zero is enough to confirm that there are vortices in the flow field. Three. Now, there's this term irrotational flow. That means there's no rotation. Irrotational flow field. Irrotational flow field means no omega x or omega y or omega z. Okay? Irrotational flow field, there's no angular velocity of the fluid element. Okay? So omega x, omega y, and omega z each equal to 0 in an irrotational flow field. Correct? Okay? So here, in third part, we're asked to derive an expression or a condition if the flow field is assumed to be irrotational. Okay, so if the flow field is irrotational, then what happened? 3, yeah? If flow field is irrotational, you have no angular velocities. Okay? So in this case, omega x equal to 0, omega y equal to 0, omega z. It's not the keyword, it's omega. Omega z equal to 0. Okay? So omega x equal to 0 from our earlier expression in part 2, we got expression for omega x in part 2. And when we found omega x is equal to half bracket 2x plus 2y minus 1. In part 2, we got expression for omega x. The omega x is half bracket 2x plus 2y minus 1. So i.e. omega x is equal to 2x plus 2y minus 1, and that is equal to 0. Okay? We also got in part 2 expression for omega y. Also, therefore, for irrotational flow, omega y equal to 0. And expression for omega y is half 2z minus 2y equal to 0. Okay? You can take out the half, so it's as good as saying 2z minus 2y equal to 0. Okay? Which means that i.e. z equal to y. So therefore, the condition for irrotational flow boils down to this expression. You have z equal to y and 2x plus 2y minus 1 equals 0. So you can therefore have 2x plus 2y. Y is equal to z, so plus 2z minus 1 equal to 0. Okay? This is a condition for irrotational flow. With 2x plus 2z minus 1 equal to 0. That's for part 3. Condition for irrotational flow. And then for 4 is under this condition of irrotational flow and using the u and v components given to us in the question, derive an expression for the stream function psi of the flow. The stream function psi of the flow. Okay, so let's recall our stream function equation for the stream function. Okay, so recall equations for stream function. U, the x component of the velocity field, is del psi del y. Okay, and d is minus del psi del x. Okay, just record. Now, from here, u is equal to L psi L y. So what is u? The given expression for u. U is x plus y plus z squared given to us. So, i.e., our u given to us is x plus y squared. So it's equal to L psi L x plus y plus z squared. Sorry. My z squared. Thank you. Z, eh? But, okay, given x plus y plus z squared, but we already have a condition in the above, in part 3, what is our z? Z is actually y. So, therefore, we can say i.e. x plus y squared is equals to L psi L y. Okay? Because we are still in the irrotational condition. Z equal to y. Now, the question is we need to get expression for the string function psi, or we can design dy. So what must we do? What must we do then? We must integrate. Next step, integrating. Okay? So integrating, what would you get? Okay, you put the L psi L y to the right, L psi L y with respect to y. You get psi. When you integrate x plus y squared, with respect to y, you get xy plus y squared over 2. Okay? And when you integrate y squared with respect to y, you get y cubed over 3. And what else? Plus a constant of integration. But when you integrate something with respect to y, you get a function of x. Okay? Remember I explained it earlier in earlier lectures. When you go with respect to y, you get function x. If you get respect to x, you get function y. Function of y. Okay? Now, we got to find out what is this function of x. So, what's the next step then? How do we proceed? Okay, let's call this equation 1. Equation 1. So, what next? Now, we are also given, we know the string function, the other expression, d is equals to minus L psi L x. Okay, d. So, let's differentiate this L psi with respect to x. So, L psi L x. With respect to x now, what you get? You get y, and the rest is this is 0, this is 0. When you differentiate a function of x with respect to x, what do you get? F prime. Okay? So what's L psi L x? From the string function initially, L psi L x is minus d. i.e., L psi L x is minus d. Okay? There. You see? There. Minus d. So minus d is equal to y plus f prime x. Okay? Now we know that d is equal to, is v equal to x? what is D?
X minus 1 plus Z.
Okay, yeah? Exactly. You have here, okay, initially we have, let's work it out here. Okay, you have U plus, here, U is equal to X plus Y squared. Okay? That's what we have. U equals X plus Y squared. We have D is equal to X minus Y plus Y. Okay? Okay? So you have, actually in this case, D is equal to X. Right? So minus D will be minus X. So okay. Now, okay. Right. So as a working, D is equal to X minus Y plus Y is equal to X from the velocity components under the condition of irrotational flow. Irrotational flow condition. So here therefore we have, since D equals X, so minus D equals minus X. Y equals Y plus X, right? X. Or in other words, rearrange. I.e. rearrange. F prime X is equal to minus X minus Y. Okay? So if we were to integrate this, you integrate F prime X, what do you get? You get Fx. Okay? With respect to X, with respect to X. So integrate minus X, you get, with respect to X, you get minus X squared over 2. And you get xy plus an arbitrary constant c. Okay, an arbitrary constant c. So if you substitute this into here, fx, we got fx here. So substitute this into this fx here into equation 1. So substitute into equation 1. Okay, to equation 1 for the expression involving psi. So psi will be all this term here plus your fx function. Fx function is given here. Alright? So let's write it there. Psi is equal to xy plus y squared over 2 plus y cubed over 3, yeah? Plus fx, okay? Plus fx. Fx is minus x squared over 2 minus xy plus c. Okay? And you just rearrange it nicely or simplify it. You get y cubed over 3 plus half y squared minus x squared plus c. So this is the expression for stream function. So you have different stream functions or different streamlines for different values of c. C can start with 0, you get 1 line. Remember your stream line? When c equal to 1, you get the next line. C equal to 2, you get x. So you get the kind of value of c that you put in, you want to sketch it out, you get a family of lines. Okay, that's a stream function. Right, that's 4. Now, 5. We have 5 and 6. 5.
detail.
Okay. 5 would be, let's do 5. Now 5 it says, divide the expression the rate of angular deformation of the fluid in 3 directions. You know that fluid structured particles, you can say any volume, the control volume, there's a lot of shear going on. So there is therefore deformation. Okay? And so angular deformation, again I'm going to introduce expression. The derivation is beyond the scope. So you just accept it, and I'll try to put the derivation of the model so you can download it and study it for yourself. So angular deformation on the xy plane, angular deformation on the xy plane, okay, on the xy plane is given by this expression here. This expression is del v del x plus del u del y. This expression for angular deformation in the xy plane, del v del x plus del u del y. And from the expressions given to us, u, v, and z, you can do the differentiation, you get 1 plus 1 equal to 2. Similarly, angular deformation, this is from a 3 direction. So angular deformation in the YZ plane, or YZ plane, okay, is given by this expression, del w del y plus del v del z. So we then differentiate the expressions given to us. In the question, you get 1 plus 2y plus 2x. Okay, so this is there, and then angular deformation in the zx plane is given by this expression, del u del z plus del w del x. So again, you differentiate the expressions u, v, and w. And given the question, you get 2, this is 2, z plus 1. Okay? These are expressions for the angular deformation in the xy plane, in the yz plane, and in the zx plane. And finally, the last part is the rate of volume dilation of the fluid. Now, the meaning of dilation means enlargement, volume enlargement or volume increase of the fluid. Because the fluid is not a control volume. The control volume is subjected to shear stresses. So when there are stresses, there will be changes, possible changes in the volume, but it depends on the flow condition. Okay? So we are therefore to derive or to determine, to find out whether there is any volume increase of the fluid because of the shear stress, because of the condition given in this question. And if there is a volume increase, what is this increase? Okay? The rate of volume dilation. So the rate of volume dilation. So there's volume change in the x direction, in the y direction, and also in the z direction. And this is given by linear deformation or linear dilation. Okay? So talk about linear dilation, which is actually the increase in the size of the fluid element. So linear dilation in the x direction is given by del u del x. Okay, linear direction in the y direction is del v del y. And linear dilation in the z direction is del W, del Z. Okay? It's related to the change in the velocity in the x, y, and z direction. So from the given expressions involving u, v, and w, you do your simple differentiation. Del u, del x will be equal to 1. Del v, del y will be minus 1. And del w, del z is 0 from the given expression in the question. Okay? The first three expressions that u, v, and w. So that is, in other words, you see this is a cube here. Imagine this is a cube. The fluid element, right? So LVX is the extension of the length of this cube in the x direction. Any extension or not? We found it to be equal to 1. Okay? And then we look at this cube. Any extension in the y in the y direction. Okay? LVY. And then the extension in the x direction. So the cube can expand in the x, in the y, and in the z direction. So that's what we found. According to the equal to 1, minus 1, 0 for this flow condition. So then what is the volume dilation? In other words, what is the net volume change? Okay? If you expand, so it expands in the x direction, it shrinks in the y direction, according to the equation here, and there's no increase in the z direction. So what's the net volume? So the net volume will be what? All these add together. Del u, del x plus del v, del y plus del w, del all these add together equal to, okay, you have 1 minus 1 plus 0. So answer is 0. So therefore, no volume dilation. Okay? No volume dilation. Alright? Okay, so we have finished this